All right, welcome everyone to another episode of GPU Mode. Today, I'm really thrilled, like for what it's worth, by popular demand, to invite like Troels Henriksen. So Troels is one of the main authors of a programming language called Futhark, which is like a very sort of, I guess if you look at the possible spaces of programming languages that have with GPUs, like Futhark is like a very, very unique take. There's tons and tons of like academic papers written about it that you can go like check out on the website. But I figured like Troels could give us like a nice crash course. Troels also informed me that he likes to be interrupted. So if you have any questions, please post them in chat and I'll be sure to interrupt them. And thank you. And Troels, please take it from here.
Yes, thank you. Right. Okay. So first of all, I want to emphasize that while I do most of the PR activity for Futhark, to use a very fancy word, it's really a group effort. I wasn't even the one who came up with it. That was Cosmin Wanscher, my eventual PhD advisor at the University of Copenhagen. And there's a bunch of other people, in particular a lot of students and open source contributors who have also contributed since then. But the genesis behind Futhark was as part of a project for high performance financial IT, because the banks were kind of bankrolling a research project, and the goal was to come up with a language such that domain experts could write high performance financial models for pricing things, because apparently it's very difficult computationally to figure out what things are worth in finance. I don't really know much about finance. I learned a little bit and then I forgot it when we stopped working on that specific domain. But the outcome of that was that we found that there wasn't at that point a language that was high level enough that a domain expert who was not a hardware expert could use it, and that was also fast enough to compute what things are worth before the regulators came and asked what they were worth. So that was interesting, and we did that by kind of reverse engineering GPU kernels. Well, we wrote some GPU low-level code for various financial problems, and then we thought about, well, how could a compiler have generated this code, and then how should the input language of that compiler look like in order for that compiler to work out, and that eventually became Futhark. So my agenda for this presentation is how we take Futhark, which is a high-level language that I'll discuss in some detail, and how we translate that to GPUs. Futhark is a kind of a broad research project where we focus on many things, also on algorithms and type systems and kind of the parallel programming in the large. But since this lecture series is called GPU Mode, I'm focusing on the GPU aspect, which is certainly an important part of the research, but it's actually not kind of the original driver. So briefly, just in case for those who do not know Futhark, which, considering that it's an academic, obscure language from Northern Europe, it's probably many of you, I'll give a brief introduction to how it works and what it looks like. So it's a standalone language. It's not embedded in any other language. It's in the ML family, and where I come from, ML means the family of languages from Milner's original Edinburgh ML. It means functional language, not machine learning, but I guess for Futhark it will actually be both. So it's very similar in structure and syntax and fields and as languages such as OCaml and standard ML and Haskell and F# and Scala and all these, although it's a lot simpler, which I'll get to. It has some fancy features like size-dependent types. It also has some standard features like parametric polymorphism and higher order functions, although with some restrictions that I will also get to. And a lot of the vision is really that the language is not supposed to be particularly weird. One of the research challenges or questions that we have posed for ourselves beyond the initial thing of helping some bangers write fast code is that we had this idea that writing parallel code and even efficient parallel code ought not to be particularly difficult. It should be doable in a language that is not more complicated than what we normally teach, like first-year students, for example. We teach functional programming to first-year students, and many universities do that, and that works out fine. And we think parallel programming should be easy enough that a first-year student can do it. Now, that doesn't mean that the language is meant for inexperienced programmers. In practice, the people who have the kinds of problems that a language like Futhark is suitable for tend to be pretty experienced programmers who do complicated things with high computation requirements. But we think the language should be simple so that they can focus on the complexity in the domain instead. And of course, it's a research project, so it's not certain that we will succeed or that we have succeeded to the extent we would like to, but I'll let you be the judge of that. I'll also mention a little bit about that later. So apart from being a pretty standard functional language, Futhark has some built-in what we call combinators, SOAX, because they're second order, which to the user just looks like normal higher order functions that are very similar to what you would find in a normal functional language. We have things like map, for example, here.
And map, you give it a function from A to B. It can be any A to B. It's polymorphic. Then you give it an array of A's, an array of n A's. This is how we write the type of arrays in Futhark. And then you get back an array of n B's. So you can see here that map turns the A's into the B's, and it doesn't change the sizes of the argument. You get back an array of the same size. And this is really just a map that you would find in any modern language. I mean, I think most languages have a map now. Now the difference is that in many languages, even languages like Haskell and ML, map is just yet another library function. It's written with recursion and so on. In Futhark, map is really something that the compiler knows about. It knows what the properties are of map, and it is able to transform uses of map and eventually use that to generate parallel code. And I'll explain that in some more detail. And there's a handful of these so-called SOACs, these parallel combinators. Like there's a reduce, which is like the reduce you would find in many other languages. It's also called fold in some languages. There's a difference between fold and reduces in the type here. And we also require that this function that you pass in here, this is a function of 2 arguments. It must be associative, so we can generate parallel code from the reduction. I'll just turn a little bit to that. And you have scan and a few more. So there's a small handful of functions that to the programmer look like functions, but have special parallel meaning to the compiler that the compiler can reason about. And then ultimately you build your programs as compositions of these primitives. These are at the bottommost level, but there's all these other nice features, parity polymorphism and higher order functions. So you can build your own on top of these. But ultimately these are what the compiler will reason about. And there's not that many for reasons I'll also get into. So what's it for? There are lots of very nice languages that are very pleasant to use for practical programming. I like Haskell a lot myself. And we didn't really set out to supplant any of those because Futhark is not a general purpose language. It's a pure language, so it has no side effects. You cannot write to a file or read from anything or connect to something on the internet. It's a pure language. You can only write functions that operate on their inputs and return some result. It cannot interact with the world in any way. So you cannot write applications in it. Instead, the idea is that you take a Futhark program, and then you compile it to a library, and then you call that library from some other language that can actually interact with the outside world through some foreign function interface. And Futhark itself will generate either C code or Python code and provide either C or Python interface, which you can then call from any language that can call C or Python code. I would say, except for Python, most languages go through the C interface. And there's some bridges you can use to make that a little bit more pleasant so it can be pretty ergonomic. But you really need some other language so to kind of help Futhark actually get something done. It really is not for writing applications, it is for writing libraries. But there's some tools where you can write small applications in sort of Futhark itself, but it's really not, that's just mostly for toys and demonstrations and examples. Now, so apart from not being general purpose, it's also not really a GPU language, which may be a bit surprising given that I'm holding this presentation at GPU mode. But again, the research perspective, and remember, Futhark, we try to make it a practical and useful tool, but we are also academics, and that means we're allowed to dream a little. So the dream of Futhark is that you can write code in a way that is high level and data parallel, and without worrying about the hardware, and it's deterministic, so you can have no race conditions. And then a compiler will make it run fast on the parallel machine that you actually have available, which can be any parallel machine because the language itself does not require you to program directly towards hardware features. Now, of course, that means someone has to actually pay the piper and find out how to make it run fast. You have to write a compiler for each machine. And of course, we don't have a good compiler for every single parallel machine that has been built. Our best compiler, and the one we've put the most effort into, is for GPUs. We have three different backends, CUDA, HIP, and OpenShell, and we work on web GPU as well. But that means that Futhark will run pretty well on GPUs and to some extent on multi-core CPUs, but it's not optimized. But the language itself is not GPU specific. It's not a GPU language. It just has a GPU compiler. It also is not particularly useful for graphics. I mean, you can write graphics programs in it because it is nothing prevents you from creating an array and interpreting that array as an array of colors. But it's not for writing graphics shaders. It is focused on throughput, not on latency. And while you can have a Futhark program that runs fast enough to produce real-time graphics, it's not really meant for it. It is a little bit painful and not really what it's meant for.
The compiler is pretty complicated. It's quite large. It's 100,000 lines of Haskell, and Haskell is a language where you can get a lot done in per line of code. So I will not talk about all that it does, because there's a huge amount of tiny fiddly things that it does in order to get the code running at all, and also to get it running well. And a lot of it is not super interesting, and it's very time-consuming to explain. So I will mostly be focusing on kind of the high-level idea of how Futhark goes from high-level data parallel code to low-level GPU kernels, and also what limitations we have because we're not doing everything perfectly, of course. And you should also set your expectations. Futhark, I think, is a pretty good language. I like using it, and it also produces code that is often fast enough, but it will not outperform expertly handwritten GPU programs. So a lot of the other lectures that you have in GPU mode that I've seen have been about all of these kernel languages, like Triton, for example, which are very low level by Futhark standards, and you can certainly write Triton code that is much faster than what you can do in Futhark. Because in Futhark, you cannot directly program the hardware. You cannot directly access hardware features. That's up to the compiler, and the compiler is not as good as an expert GPU programmer. Now, of course, I would argue that Futhark is easier to program in than many of these modern kernel languages. In particular, if your main goal isn't to get a matrix multiplication or something running as fast as possible, but if you're prototyping new parallel algorithms and you just want it to run faster than if you wrote it completely sequentially or in Haskell or some other very high-level language. So Futhark is fast for the kind of language that it is, for the kind of high-level functional programming that it provides. It is not fast compared to real low-level languages implemented by expert. Now, in my experience, most GPU code is not super expertly written, and Futhark will definitely beat GPU code written by someone who's not very good at writing GPU code, which is many programmers. And one other very important thing Futhark gives you is that it optimizes the composition of things. So many of these other languages that makes it very easy or possible to write very high performance kernels, they don't make it very easy to write high level components that you can combine together and then also expect that the result will be fast. Whereas Futhark is supposed to be a normal language in the sense that you can write libraries and reusable things and plug them together, and then the compiler will try to remove the overhead of having written things separately. So you can write normal, small modular components that are plugged together and still get good performance. That's one of the goals, one of the kind of advantages of using a language like Futhark. So, I mean, I usually phrase it like it has to be faster than everything that is more productive and more productive than everything that is faster. But I think pretty much every language tries to be on that curve, because otherwise it's just objectively worse than something else. And the difference really is just where on the curve Futhark tries to be. It doesn't aim for maximal performance on GPUs, because then we would have gone for a more low-level GPU language. It goes for maximum performance with the constraint that the language should still be hardware agnostic. But that also makes it interesting how we actually map these high-level concepts to GPUs. It's not a goal to taking over the world. You cannot write everything in Futhark, and that's fine. I like many other languages as well. So you only use it for writing small performance-sensitive parts that might be more than one kernel, as we will see. A Futhark program might turn into several kernels, but it will still be a fairly small part of a large application usually. Okay, so let me show you some examples of Futhark code just to get an idea of what Futhark programs look like and how they feel. And that's partly to get an idea of the syntax, which may be unfamiliar to some of you. It is a very conventional syntax from a functional programming perspective, but if you're not a functional programmer, it will look a little weird. So this is an implementation of softmax. So the first, I have defined a function, row softmax, for computing the softmax of a single vector. That is written like this. I don't have a size here because I don't care about the specific size here. That'll be inferred by the compiler. It's a vector of single position floating point numbers. So the first thing I do is that I find the largest element of that vector with a reduction. And so in Futhark, as in many functional languages of this kind, we do function application just by putting a function next to an argument. We don't need to put parentheses. So this is applying the function reduce to the three arguments, f32.max, that's a function, f32.lowest, and an excess. So this does a reduction where this is a neutral element, and this is the operator. So we are finding the maximum element of this excess. Of course, in a real program, there's a function that is just find the maximum element of a vector that you can use instead. But here I'm writing it using the fundamental components reduce, so you can see how it looks. Then we get back an x, max x, which is just a float, an f32. We can then map on top of the original vector. For each element of that vector, x, we can run some code that produces a new element. In this case, we take x, we subtract max x, and then we take the exponent, and then that is going to give us a new array, exps, also of this type. That's not visible here, but it is an array or a vector of f32s. Then finally, we sum that using a reduction, where now we use the plus operator with 0 as an initial element. And then finally, we divide every element of this exp array with the sum. So that is softmax on a vector. To then do softmax on a matrix, we just take our matrix here, M, which has 2 dimensions, and then we map the row softmax function on M. That means on every row of M, we apply this function. And you can see a row has this type, the function accepts something of this type, that's the same thing, returns a new row or vector, and that means that the result of the map will give you back this. So this also shows how you can do composable programming. You can write a function that operates on a single element or a single row, and then you can easily map it on top of all of the rows of a multi-dimensional array, like so, just with map. So that is composition, and then it's up to the compiler to figure out how this actually turns into efficient low-level code. As another example, here is matrix multiplication, which I have heard many people care about. I can see I have a typo here. This should be the same type. So first I define a function dot product that takes 2 vectors. And then I do a element-wise multiplication of those components. So the first element gets multiplied with the second element and so on, using a function called map2, which is just a library function built on top of the fundamental map function. So this is something that you could write yourself. It's just simultaneously mapping on 2 arrays at the same time. And then you sum the result of that. That is just a dot product. Then to define the matrix multiplication, so that these should be F64s. This should not be integers. And to define the matrix multiplication, we can write that as mapping over the rows of the A matrix, then mapping over the columns of the B matrix, and we do that by mapping over the transpose of B. By default, Futhark assumes row major, so by transposing B, we can kind of get a column major. We map over that, we get a column of B, and then we just take the dot product of the row of A with the column of B. And again, we are able to reuse the dot product here, down here. And another interesting thing here, I said this was not going to be my focus, but Futhark does have this nice little size type system. We can see that this function here is parameterized over 3 sizes. These are not things that the user will pass explicitly. You can see when we use dot product, we don't pass in an n here, we just pass in the actual vectors. Now these here are used for expressing constraints on the function arguments. In dot product, for example, it is used to enforce that the 2 arguments must have the same length, because that is the definition of dot product requires that. For matmul, we require that the number of columns of A must equal the number of rows of B, and we get back a result that is the number of rows of A by the number of columns of B. So you can kind of express these fairly common constraints directly in the type system, and if you write a program that doesn't obey these constraints, you will get a type error rather than a runtime error. This is something that is really pleasant when you're doing linear algebra-ish stuff, and really means that the computer complains about your code long before you run it, which is nice. Finally, this has nothing really to do with GPU program or parallelism. Futhark also supports standard functional programming things, so you can define a type of an option type that is polymorphic in some element type A, and say, well, an option is either some A or it is nothing. This is just an option type or maybe type or whatever it's called in other languages. And then you can use it, for example, to define a safe indexing operation where you give it an array and you give it an index. And then depending on whether that index is in bounds, you get back either some or none. So this is just to show that Futhark is high level enough that you can use normal functional programming techniques to write some types and so on, which is very convenient for some applications. But there's nothing really to do with parallelism. This is just a nice little feature. Okay, so Futhark does a lot of things that are pretty standard for function language. You can
Troels,
write all of, yes, sorry.
sorry, no, I have a bunch of questions, if that's okay. But if you want to finish your train of thought, that's okay. Okay.
No, just-
So the first question I had is like if you could go back to the Matmul slide.
Yeah.
Actually, yeah, there's a logistical question. Someone in chat is asking if you can make the font bigger. Presumably not, because these are images.
I can. Oh, sorry.
Oh, wonderful.
Yeah, it's so this is these are just text slides. I just increased
Oh.
the font size. My term, no problem. This is
Okay.
Okay.
Okay, this is wonderful. Thank you. As I looked at something like this, and I was like thinking, oh, like let's say you're trying to implement something like swizzling, like presumably that's like yet another function, and expressing layout transformations is quite easy with a programming model like this.
Yes. Yes, whistling, that's just, I mean, changing the elements of a vector or an array from Futhark's perspective. Of course, the real challenge is can you map that efficiently to hardware? But semantically, there's no challenge in running a swizzle operation.
I see.
Because you're just indexing.
Okay, and so like the other question is like, I mean, you obviously referred to other programming languages that are like, one of the things you mentioned is like Futhark is a pure language, and so the main thought that popped in my head is like, well, how do you deal with determinism and randomness? Because like at least like within like the CUDA ecosystem, like most Cudean algorithms will not be deterministic by default. Is this like something you care about? Is it like a property of the emitted code, or is it a higher level property that you need to reason about? And anything to say that?
Yes, so the language itself is completely deterministic if you ignore certain things like if you do a summation on floating point numbers, it doesn't specify the order, so you might get some non-deterministic round off. I think that, but apart from stuff like that, it is fully deterministic, which means if you actually need randomness, you need to use a standard functional programming tricks to get them, which usually involves manual management of a random number generation state.
I see. Okay.
And you do that in a very conventional way. In the actual way, the field of programming in Futhark is very similar to programming in something like OCaml, or the pure subset of OCaml.
Okay, I see. Okay, I have a few more questions, but maybe we'll go through them later. Thank you, Troels.
Okay, yeah, sure. Okay, so, but none of these features are actually something you wouldn't find in other languages, except maybe for the size type stuff. But the thing that makes them really difficult to implement is that Futhark also wants to be fast. And when you want performance, that is a feature that makes every other feature much harder to implement. So we had to constrain Futhark a lot compared to languages like OCaml or Haskell in order to make it feasible to write a compiler that can guarantee that it will generate code that is good, for some notion of good. And of course, here the trick is to come up with restrictions that provide the maximum benefit to the compiler and the least amount of bother to the programmer. And I think we managed to do this all right. Some of these will look a lot higher, quite harsh initially. So the main restriction, which is very unusual for a functional language, is that we don't have recursion. You cannot write a recursive function in Futhark. And this is simply because we want to target hardware, like especially GPUs, where unbounded recursion is just way too costly. There are techniques for implementing it, but they result in slow code. And we don't see any point in having a language designed for performance where there's a feature that if you ever use it, your program will just be slow. That seems kind of contrary. So it's better to just avoid it so programs will not accidentally write code that doesn't actually do what they hoped it would do. Now, because sequential iteration is kind of important, we do have a special bit of syntax that corresponds to a tail recursive function. That is those functions that are recursive but don't need a stack to be recursive, where they just call themselves. So this is a notation. It's not super important for the rest of the presentation. I don't want to show it. You have to have some loop parameter x. It is initially 1. Then n times you run the loop body where x is the parameter, so it has some value. And then the result of that loop body is bound to x, and then the next iteration runs. So this will see n times you can have to imagine there's an x equals x times I, or assign x to x times I if you want to take the imperative reasoning. And this could also just as well be a while loop instead of a for loop. But that is just what Futhark has for sequential iteration. This particular syntactic sugar for tail recursive functions. Another restriction that a functional programmer might also balk at is that it does have higher order functions, but they're not completely first class. And that is because the standard way of implementing first class functions in pretty much every language is that a function, first class function, is a pointer to a function. So when you want to call that function, you have to follow the function pointer. Now you can have function pointers on GPUs, but again, the performance implications are at best unpredictable. So we don't really want to go there. I'll return to what those restrictions actually are. A final restriction is that we don't have irregular arrays, which means that you have an array that is multidimensional, then all of the inner dimensions must have the same size. For example, this array here, where the first element has 3 elements and the second one has 2, is not allowed. You will get a type error if you try to have a constructed program that would construct such a thing at runtime. We have an entire type system for ensuring this cannot possibly happen. And the reason for this is that we want predictable layouts and easy allocations. We want to be able to say that, well, we have an array of multi-dimensions, it has a shape, we can just multiply together the shape, figure out how much memory that needs. And we can easily reason about how it's laid out in memory by having by doing there's various formats for representing array layouts. But they all depend on having some kind of predictable layout. I mean, and the classic predictable layout is the square array or rectangular array where every sub-element has the same shape. There are also some other layouts that you could also use, like triangular arrays, but you cannot have those directly in Futhark. That's something you can work around yourself. You can model your own irregular arrays, as we call them in Futhark, but at the fundamental language level, they're not allowed. You have to use regular arrays. And then you can encode things into a big one-dimensional array if you need it. Okay, so let's talk a little bit about the value representation in Futhark. Because it's a function language, you can have various things. You can in particular have numbers. And Futhark by default unboxes everything, so you don't have to follow a pointer all the time. That's of course crucial to get any kind of performance on a modern machine. Everything is called by value because it's pure language, except arrays, which are passed by pointer. And if you have things like a triple or any kind of tuple in Futhark or a record, then in a normal language, there would be some boxed struct that is kept somewhere, maybe on the stack or something. Futhark will actually just take this apart and treat it as 3 distinct values. The compiler itself has no idea what a triple is or a tuple. It's just separate values all the time, which can be kept in registers, as if you just had 3 integers that happen to be floating around. Of course, one challenge is that Futhark has pretty flexible arrays, and you can have arrays of anything. In particular, you can have arrays of tuples. So consider if you have an array of pairs where the pair consists of a 32-bit integer and an 8-bit integer. Now that's a 4-byte value and a 1-byte value. And then the perennial question is, how should we actually store an array of this type in memory? So the packed form would be something like this, where an array has this format. It has some starting offset, then there's a 4-byte integer, then there's a 1-byte I8, and then immediately after that, 5 bytes after the start of the array, you have another integer and then a byte. And this doesn't waste any memory, but the axes here are unaligned, and that's pretty bad. What this integer here will start at an address divisible by 5. And that is at best slow, and at worst, it just doesn't work on hardware. It will give some unaligned axis error. Another way you could solve this, of course, is how I think a C compiler by default will do it, by padding up the struct to some alignment size. So that, of course, unfortunately, that wastes memory. So now you use 8 bytes of memory per element, despite only really having 5 bytes of real payload. So we don't want that either. So the solution we use, which is a standard solution for this kind of problem, is that whenever you have an array of tuples, then that is represented internally and at runtime as multiple arrays. So instead of having one array of a pair of T1, T2, T3s, you have an array of all the T1s, an array of all the T2s, and an array of all the T3s, and they all just are laid out tightly and compactly in memory. Now, this is it's completely standard transformation in high-performance computing. It's often called the structure array transformation, and all of you who've done GPU programming have probably done something like this as well. And it kind of sucks very often because you often end up having to break modularity to do this, because it's kind of an invasive change. The Futhark compiler does it automatically behind the scenes, so you can program using arrays of records and a kind of rich, large objects, or well, not in the object or in a sense, but as large values. And then behind the scenes, the compiler will turn it into this representation instead. It's not visible to programmers at all. It just happens completely automatically, which is very nice, because it can get quite annoying to do this by hand, especially when you have things like polymorphism and so on, and you don't actually know what type you are going to end up with at runtime. All right. Another problematic thing, I mean, everything is problematic when you want to run on a GPU, as I learned when I first started on this project. Another problematic thing is high order functions, as I mentioned, because they're normally implemented with function pointers. And yeah, you can have them on GPUs. I don't actually know what the full state of the art is, but just blindly using function pointers is going to be bad. You're going to have divergence and all kinds of nasty things. And even on CPUs, because we also want to run fast on CPUs, having your program be just a long chain of indirect calls through function pointers is probably also going to be pretty slow. So we would like to not end up in a situation where that is the only way we can run the program that the program has written. Fortunately, we're not the first people who dislike function pointers. In the 70s, there were also people who didn't like function pointers either. And this is not because they needed to get their code running on NVIDIA GPUs, but they wanted to apply some static analysis techniques that could not cope with higher order programs, which means programs that have higher order functions, which is kind of equivalent or isomorphic to our challenge with function pointers. So John Reynolds, back in 1972, made a great contribution to GPU programming when he invented the idea of defunctionalization. And the idea is that you take a high-order program, that's a program that actually has first-class functions, and you transform it into an equivalent program that does not have first-class functions. And the basic idea is that you take every function term in the program, that means any lambda, this is a lambda with a parameter x, and this is a body x plus y, so an anonymous function of one parameter, and you turn that into, this is a compiled transformation, you turn that into a value that has some unique tag, 0 here, that represents the original function body, and then contains the free variables. You can see here y here is not a parameter, so that's kind of some free variable that is defined out here maybe, and you store that inside. This really represents the closure corresponding to this function. Similarly, if you have had two free variables, k and z, you would have two values here, and this would be, you have a different number because this is a different lambda. Then when you apply a function, then you know that any function will now be something of this form. And then when any function call can be replaced by a big case statement where we just check, oh, this function we are going to be applying, is it this function? Is it lam0? If so, we do this, do the a plus y corresponding to what's going on up here. See, a is the concrete parameter of the function call that replaces the x. Or maybe it's the other function, and you just do that. So every function call becomes a big case, a big control flow where you check which function is this actually. So this helped John Reynolds a lot in 72 because his static analysis technique could cope with branches, and these are because his problem was high order functions, not branches. But this is still not good enough for us because sure we can get rid of function pointers, but at the cost of having a big case in we apply a function. And also, if you have arrays of these things, that they quickly become very irregular because then the data you store for every element can vary a lot. So that's also quite inefficient. So what we do in Futhark is that we apply some restrictions in the type checker to ensure that we always know which function is being called. That is, when we have that big case, we will know statically which of the possibilities it must be, which means we can of course elide the case entirely. So let's look at some cases where that will prevent us from knowing that. Here's, for example, a case where we have an if, and depending on some Boolean values, we return one of several functions and put that if, and then we apply if. Now, in this case, we have no idea what f might be. Which of these are actually going to be applied here? We cannot decide statically because that depends on these runtime values, this b1 or this b2. So we introduce a rule saying a conditional cannot return a function. Okay, what else? Where else can it go wrong? Oh, you can have an array of functions. So you have an array here of this function and this function, maybe some more functions. Then you can index an array based on some runtime value I and apply that to an argument. Again, we have no way of deciding or knowing which of these functions is going to be applied without knowing what I is, and that's runtime value. So again, we introduce a rule saying you cannot have arrays of functions, which is kind of a harsh constraint, but it saves us from this problem. And with these two rules, and an additional one that is not so important, we will get the guarantee that we can always decide statically, whenever a function is applied, which function that is. So you get the feeling of programming with higher order functions, but with some strategic constraints. That means the compiler has a much easier job. So this is essentially how it will look like. This is a demonstration of defunctionalization. So we have bind some numbers to some variables, then we construct a lambda but adds a to his argument x, and then we apply that lambda. Now, with defunctionalization, this lambda here, that turns into a record that just captures the free variables. That's just a tuple, you can say, that captures the free variables of use, just the a here, and then the application here becomes a call to a lifted function that is provided, the closure here, and then the argument, and the lifted function then extracts the free variables from the environment, and then it just does what the function was supposed to do. And this works out quite nicely. This results in a program. You can see there's no control flow here. It's just straight line code, and that's something that we really like. And then, of course, we have to make sure we handle this tuple efficiently. This is essentially just a tuple, and that's done by just pretending there is no tuple and turning it into separate values. So that ends up resulting in quite nice code. Essentially, the code that you would write by hand if you manually specialize all of your higher order functions. So the point of that is that restricting the language enables better code generation. And what is crucial, I think, is that these restrictions are easy to understand in the sense that they are expressed in terms of type rules. They're not just based on the compiler running some magical analysis that you don't understand, and then sometimes saying no for reasons that you cannot comprehend because it's a decision made by some black box. It's composable because it's expressed in the type system. So you need, of course, learn how the type system works, but it's not going to be particularly magical. The rules are not going to crop up at runtime or only appear once you're trying to combine things. They kind of appear immediately when you break them, not later, not due to composition of things. And in practice, we have found that for the kinds of programs that people want to write, they are not so much of a hindrance. The only people I have noticed who run into them are experienced functional programmers from other languages whose favorite programming styles may not work so well in Futhark. But for people who come to it from outside functional programming, they usually don't even notice that these restrictions are in place because they don't really crop up for standard styles of programming.
So, Troels, I think maybe this is a good time for a couple of questions. Okay, so first off, I want to ask you a bit more about defunctionalization and like when it comes up. Like, I think a very natural scenario for me is something like I have a matmul that I want to fuse into some pointwise op. I don't like the compiler, like I can't have a generic function that goes fuse matmul and then some unknown generic pointer at runtime. And so with defunctionalization, like I can have like the optionality of calling all of them. Is that like sort of a very, like at least for machine learning people, like would that be like a good motivating example?
Yes, or even you can have a matrix multiplication that is parameterized over what multiplication means. That's just another higher order function.
So okay, I see. So whether you're doing, for example, a matmul over like where you're doing the inner product basically over. Okay.
Yeah, yes. So, and those always have the property that the function sort of flows downwards. And it turns out that if your function flows downwards, then you will not notice these restrictions. They will not affect you whatsoever.
Okay.
So that is the main reason why.
Another thing I want to ask you is like the term like so at least within ML compilers, there's a very popular term people use called functionalization, which like if you have frameworks like PyTorch, effectively you can have in-place mutations. And so what they refer to as functionalization is writing your code such that you remove in-place mutations and you make everything functional.
Right.
Is this concept related at all to defunctionalization, or is this like just an abuse of terminology and they're very unrelated?
No, it's not. I don't think it's abuse of terminology, but it's just the conversion devolution of nomenclature. I mean, it's just about what they are both rooted in the word function, but no, they're completely unrelated. Defunctionalization has nothing to do with whether you have side effects or not.
Okay, I see. Okay. So the last question was like you mentioned like some important restrictions on like statefulness, and I think like at least like within machine learning, there's sort of two very natural places where state comes up. Like one is the weights of your model, which I figure the workaround is you have a function that just returns the weights of the model. But then you also have things like KV caches where like also I don't mean to put you on the spot because you did mention your applications are different from like what someone might do with like let's say ML stuff. But like let's say for these two use cases, where are paper cuts you potentially foresee with Futhark, if at all, for KV caches and model weights?
I don't. So the caching issue. So Futhark has one very big limitation that I'll return to a little bit, which is that you cannot have benign effects. And caches are kind of a benign effect where they only exist for performance. You're not supposed to observe whether another thing is in the cache or not. That just makes the program faster or slower. And Futhark does not know what a cache is. Futhark's restrictions on purity are very harsh because it doesn't really understand what you're doing. It has no domain knowledge. So you cannot write those kind of benign effects in Futhark, unfortunately.
I see. Okay.
Now, but in many cases, it turns out you don't need them. And part of that is because Futhark does actually have a feature that I am not going to talk about, which is called uniqueness types. And it allows you to do local imperative things where you get the performance. Imperative like before, you can override things. You can override elements of arrays in an imperative-ish way and get the cause you would expect that just does a write directly. And then the type system guarantees that you can never observe that this is imperative. So you will never use the old array again, for example. That's a really subtle feature, and it can be used. It specifically exists to handle these kinds of algorithms that require some kind of operational destructive updates. That's a complicated topic on its own, so that's why.
That sounds. I mean, yeah. Like, I'll maybe reach out to you after the talk to just get a link to if there's a relevant paper. I think that sounds super compelling to me.
Yes,
well, I'll let you keep going. Thank you, Troels.
Okay, so most of the complexity. Now I've been talking a lot about language design. Now let's move on to what the compiler does. So it's a big compiler and does a lot of the classic stuff like constant folding, inlining, and so on. But for the purpose of this talk, I'm not going to talk so much about that. I'm going to talk about the optimizations that are important for GPUs and that kind of relate to how GPUs work. I will mention one general purpose optimization that is technically not GPU specific, and that is Fusion. That is because Fusion is the single most important optimization for making these very high-level data pro languages work. So the basic idea behind Fusion is that if you have two adjacent operations, then you can smash them together, so you don't need to manifest intermediate results. And all of the ML compilers do this as well. This is kind of table stakes. So here's an example of how I would express it in Futhark. If you're first mapping G on some array XS, and then you're mapping F on the result, then Fusion is turning that into a single map where you get the elements of the array, and then first you apply G, and then you immediately apply F on the element without writing the result to memory first. So that's important because it means you read and write less from memory. And it's also crucial because it enables different kind of programming. It means you can write small functions and then compose them without paying the overhead of having to store the intermediate results. And Futhark has a pretty fancy fusion engine that can do all kinds of fusion between different combinators that the compiler knows about, not just map. But I won't talk so much about that because that is, again, a big topic by itself. But the important thing is just remember that in Futhark, you're not penalized for keeping things small. The compiler will mesh it all up together into a big ball as best it is able. And this is pretty good at it. Now let's instead talk about how these parallel operations, these high-level things, actually map to GPU code. So the main important thing here, which I think will not be so much of a surprise to this particular crowd, is that Futhark is not a parallelizing compiler in the sense that it tries to guess which of your loops are parallel. It depends on you using parallel combinators to express where the parallelism is, and then the compiler will just try to figure out how to best run that on whatever hardware that you have available, which is only GPUs for this talk. And to a large extent, it is pretty obvious how it will do it. For example, you have a map. That means apply a function to every element of an array. It is not difficult to imagine that a map can just be turned into a GPU kernel with one iteration per element of XS. And I want to introduce a little bit of notation here because just to make it clear the difference between map as a high-level concept and the map that occurs when the compiler has decided, well, this map is going to turn into a kernel. I'm going to call that a segmap thread. And the segmap thread, you tell it essentially the grid size in threads, not thread blocks. In this case, it's a one-dimensional grid of n threads, and then every thread will run this function. So it will be given its ID and I, which will be in the index space of n, so from 0 to n minus 1. And then you can use that to index some array to get out an x, and then it can do whatever the function here is supposed to do with the f. And of course, this part can also be complicated because maybe there's some allocation in there that needs to be expanded and so on. But the basic idea is not so complicated. A map just turns into a segmap thread with one thread per element of this array. That's a simple case. Now, if you nest maps, then what do you do? So if you have perfectly nested maps, and by perfectly nested, I mean that we are taking a two-dimensional array, XSS, That means we are mapping. We get back an X. We have a get an XS. That's a row, and we just immediately map that row again. So we have a stack of maps, and then here we're doing something with the elements. Then that turns into a two-dimensional seg map thread, which we write like this. And if XSS has shape n by m, then we will need n by m threads. And this should be, sorry, I have a small mistake here. And then there are two arguments here, I and j, corresponding to the index space, where you can then index XSS to get the X that you want, and you can apply the function here. So the basic idea here is just for these perfectly nested maps, you can turn that into a segmap thread, and the segmap thread is pretty easy to turn into actual low-level GPU kernel using whatever API you prefer later on in the compiler. That's pretty mechanical. That might not so interesting. It happens very similar for reductions. So a reduce operation with some operator and some neutral element and some input array is turned into something called a segwed thread. And again, we assume if XS has n elements, then there's an index space of n. This is the operator, this is 0 elements, and there's a little function here that just indexes the array here. And then this thing, segwed thread, that can also be turned into a GPU kernel. It's a little bit more complicated because this is really a challenge of how do you generate code for an efficient parallel reduction on a GPU. And you just need to teach the code generator how to do that. So we did that some years ago. We continue to maintain it and improve it based on how GPUs change. But basically, the compiler just has to have a recipe for how this construct here should be turned into efficient GPU code. So that's where the effort gets put in. As long as we can eventually turn the program into compositions of these, then the code generator can turn that into effective GPU code. This also becomes one kernel, maybe two kernels, depending on the algorithm you use for this segwed. When you have a map on top, you just add another dimension. Sorry?
So Troels, yeah, speaking of reduction algorithm choices, like, is this like something you expose to people? Because like these different algorithms have different trade-offs between like, is it reproducible? Is it fast? Does it have atomics or not? Do you care about launch overhead or not? So like, I'm sort of curious how you expose these knobs to end users.
No, these for reductions, these knobs are not exposed. There are some knobs later that are exposed in some sense, I'll return to, but the compiler just does the best it can, but with some assumption. For example, it doesn't optimize for launch overhead generally, but it will in some cases. But no, it's a black box compiler. It is not particularly configurable. This is not core to the design. It's just mostly an issue of how many resources we have available to invest in this maintenance. It is much more difficult to have a compiler that can do many things than one that does one thing.
One thing, well, yeah, makes sense.
But the important thing here is that we can also have segmented things. So you can also do a reduction on a multi-dimensional index space, which corresponds to having a map on top of the reduce, or really any number of maps, where again you have multiple elements and you pass and you just index some array based on that. Now, when you do this, you don't get a single element back. Like this segment here, that's a reduction on a single dimensional index space. You will get back a single scalar as a result. Here you will get back a result per outer iteration. This is essentially what is also called a batched reduction. And this idea that all of these, that's what the seg part of all these constructs means, that you can have any number of batches on top, and the code generator will know how to turn that into efficient code. Now, the way that you turn this into a good GPU kernel and the way you turn this into a good GPU kernel are actually quite different. So that's very completely different code paths finding these two cases, because this is a batch reduction, this is not a batch reduction. But this is ultimately just essentially hard coded into the code generator. And there's a small number of these constructs that the compiler knows how to handle, like 4 or 5, depending on how you count, and they do the best they can. Like for scans, it's just the fancy decoupled lookback, depending on which GPU backend you're using. We also have a really fancy way of handling histograms and such, but that's just a small handful of these. But of course, the program that the user writes might not look so nice, because Futhark is very general. You can map with any kinds of functions that you can imagine. For example, you can have a map that looks like this, where you have some two-dimensional array, and you're mapping a function, and for each row, you are finding the max of that, and then you are dividing each element of the row with the max that you found. So this is not normalizing every row of a matrix, really. And this particular map here, that doesn't match any of the templates that I just showed you, because they were all a map containing either a single reduce or a single other map or a single other small operation. And that doesn't fit So the question is, this particular thing, how should we run this on a GPU? And this is actually a really big challenge. This is perhaps the main research challenge in FUSAC. How do we map nested data parallelism to the parallel levels of a concrete machine, like a GPU, but it's also a problem on CPUs. Now, the GPU's problem is particularly acute because they are not fork-join machines. You cannot just have threads that launch more kernels. Well, you can, but the performance implications are tricky, so we don't want to just always do that. So our solution is that we have a transformation we call flattening or fission that cuts apart these complicated map nests until they fit simple patterns that the code generator is able to recognize. And then we can fall back on the efficient code generation. But it's all based on cutting apart these map nests into simpler map nests. So suppose this is what we have initially. This is the program we had before, map with some complicated stuff inside. Then we can cut it apart here. We can distribute this statement and this statement such that we have two map nests, where the first one just does all the reductions and returns an array of n intermediate results. And then in the second one, we map over simultaneously. This is kind of, can map over two arrays at the same time. We map over both the original array, XSS again, and the intermediate results we had, which should be the S. And then we can, let me fix that to make it clear. And then these particular things, these look like the patterns that I showed you before. These are a map with just a reduce, or a map with just a map containing some sequential stuff. And these can be then turned into the segmap thread construct that I showed you before and turned into GPU kernel. So this becomes one kernel, and this becomes another kernel. So this is what it would really look like if you use that full notation. But of course, the question is, did this actually make the program better? Because an alternative would be that we just said, okay, we're just going to launch one thread for each of these maps, and then each thread will do this reduction and then do this map sequentially. Because reduce and map, I mean, they allow for parallelism, but there's no obligation that just because we have map in the program, that has to be parallel. That's a performance trade-off. Maybe it's not worth parallelizing that part. So is this thing, this transformation here, where we maximize the amount of parallelism, really maximize the amount of threads we could put on the GPU, does that actually make the program faster? Because that is, after all, the ultimate goal, not just to heat up the GPU. So another option is, as I mentioned, that we make it partly sequential, where we only parallelize the outer map and we leave these things as sequential code and get turned into imperative for loops or what have you later in code generation. And we just have n threads. Another option, a rather fancy option, is that we don't launch one thread for each of the outer maps, but we launch one thread block. So now we launch n thread blocks. Now we're using a construct called segmap thread block instead of segmap thread. And then inside of each thread block, we then collaboratively perform a reduction and a map again. Now, the advantage of this approach is that the intermediate results here can be stored in shared memory on the SM. It doesn't have to go to global memory. So it's going to be quite fast. If, of course, these operations, which produce arrays, operate on arrays of size m, will actually fit in shared memory. So now we have three different versions. One that fully exploits parallelism, one that partially exploits parallelism, that's this one, and one that kind of cleverly tries to exploit locality, but may not fit depending on what the size of the actual array will be at runtime. And it took me a little while to accept that there is no one-size-fits-all for these kinds of programs. So what the FUSAC compiler really does is that it generates all of these versions. They all do the same thing. They're all semantically equivalent. They produce the same result. They just do it in different ways and have different performance characteristics. So the compiler will generate a big if that contains all of these versions, and then it will pick at runtime the one that it thinks is best based on a combination of heuristics and some other decisions. For example, it will say that if the amount of parallelism in the outer dimension exceeds P, which is some number that represents you need this many threads to fully utilize the GPU, then it will not exploit the inner parallelism based on the idea that parallelism is not free to exploit. So if we can fill up the GPU without exploiting it, then that is the superior option. Otherwise, if we don't have enough parallelism here, that means we need to exploit some of the inner parallelism as well. Then it'll see that, well, if that parallelism fits inside of a single thread block, then we are going to use this segmap thread block version where we exploit more parallelism, and it also has good locality. But in In case this is not true, in case the inner parallelism does not fit in a thread block, then we need to fall back to the fully parallelized version that uses local memory for intermediate results. And now P and B are hardware constants, and P you can determine by auto-tuning. We wrote a paper about that some years ago. You just give the compiler some representative data for your program, then you run the auto-tuner and go away and get a cup of coffee, and it will find out what the optimal value of P is. And actually, there are actually multiple P's. Every single instance where it does multiversioning will result in a new P, because the P might also depend on what goes on inside of these bodies. It turns out to be quite effective, this transformation, but it does mean that the code size does increase significantly. This really gives you there's some pruning and such, but in the worst case, you get an exponential increase in code size, exponential in the maximum depth of your parallel nesting, which is usually not that big in practice. So your program will not completely explode. Exponential sounds worse than it is, but that is a trade-off. You will get a larger program. Of course, we have some heuristics for not generating versions that are meaningless, and you can also add some attributes to pick the one that you intend if you know what you're doing. But that is a trade-off here. Another interesting thing that the compiler does, which is also related to this idea of modularity, is that it will automatically try to optimize your array layouts based on how you're accessing them. So here, for example, is a kernel that launches n threads, and each thread will then sequentially traverse some array, xs, which is a two-dimensional array. So because we assume that in Futhark by default arrays are row major, this is going to be the fastest varying index, the j here. It's bound here in this for loop. So that means we're going to have uncoalesced accesses, because each thread will be going through memory with a stride of 1. That's bad, of course. That's just standard GPU nastiness. The way the Futhark compiler fixes this is that it notices these patterns and determines that this is not an efficient access pattern for this array, assuming it's row major, and then inserts a transposition of that array to make it column major, and then we access that instead, and flips the indexes here. And now the accesses actually are coalesced, because now we can see that each thread jumps with a stride of n, I guess, or m, depending on what it is, and neighboring threads will access the neighboring elements in memory. So this is a standard coalescing optimization, and the cost is just doing this transposition. But if you have an efficient transposition kernel, then you can do that in the cost that it takes to copy the array, essentially. So in many Futhark programs would actually spend more time transposing arrays to make sure that the memory accesses are all coalesced, and it will actually then running the subsequent code just as long. This is definitely worth it. And of course, in some cases, the compiler can further optimize and look at, well, where does this excess come from? Maybe we can just construct it immediately in column major form, wherever it comes from. But in some cases, that's not possible, or you just move around the problem. But these transpositions are usually a good idea. So that's also part of this idea of modularity, because when you write a Futhark program, you don't have to worry about whether you're storing your results in the optimal order. You don't have to worry about how your users of your function will want to access memory. You just construct an array and assume that the compiler will kind of handle make sure the layout is optimal based on how it's used. Now, I mean, optimal is a big word here. This is not a super advanced analysis. If you do things like your own index arithmetic and weird calculations, then it doesn't understand what you're doing. If it doesn't understand what you're doing, then it's not going to touch it. It will assume that you know what you are doing. But for simple things where you are straightforwardly iterating entire dimensions of your multi-dimensional arrays, then it is able to understand what goes on and lay out the arrays in an optimal way, or at least in a way that is coalesced. Okay, so that's a bit of how the Futhark compiler works. One question I always get is, who actually uses this? I mean, this is an exotic, obscure research language. There are not that many people who use it. The people who use it tend to be either hobbyists, dreamers, or students of data parallelism. Some of these students are my own, who are forced to use it. Others are students at other places who are sometimes volunteers to use it or forced by their own teachers to use it. But there are also people who use it who are not hobbyist dreamers or forced to. And that tends to be people who are researchers, not in compilers, and usually also not in machine learning, because machine learning users have their own languages. But there's been people who need to implement complicated algorithms that are not easily expressible in the high-level languages that they have available, like JAX or PyTorch, and that are too hard to express in low-level languages like Triton or just CUDA itself. but also want that performance that they would not get if they wrote this in Haskell or OCaml. So that Futhark is in a kind of a sweet spot in that you can write pretty advanced stuff and it'll still run pretty fast as well. So one example that I like is that as a Swedish engineering researcher, mechanical engineering researcher, I think, who wrote a unusual neural network for particle simulations that apparently was difficult to express in other languages. And it's also a pretty large program. And very importantly, he makes use of Futhark's support for automatic differentiation, which is a very exotic feature that you will find in machine learning languages, but not really anywhere else. But Futhark does have it, and it's some kind of a killer feature when you want to do that kind of stuff, because differentiating large things by hand sucks. Okay, so what's next for Futhark? It does actually work. It's a pretty nice language. I like using it, especially for prototyping things, because you can write things in a fairly natural way if you're a function programmer at least, and its size types help you, and you can run it on a real GPU and see what happens. So the research challenge that we're still exploring in Futhark is to see how far we can take high-level deterministic data parallelism as a program model. We know that there are things that you cannot do in it. The question is, what can you do, and can those remaining problems be fixed? So one question here is, what can we express? And another is whether we can generate efficient code for it. I think the latter is perhaps more interesting for this audience, because there are things that Futhark does not do so well. It has a pretty simplistic view of what a GPU is. And there are things that modern GPUs can do that Futhark does not utilize to its disadvantage. In particular, it does not use any kind of asynchronous operations at the kernel level, like for overlapping memory and compute, which is crucial if you really want to get that last bit of performance, of course. And you can do that in these low-level languages, but it's not really clear. You probably should not expose this at the service language level. So the question becomes, when the compiler should it try to exploit this? It also doesn't use tensor cores and similar specialized operations, again, because we don't have that in the source language. So we need to come up with some kind of compiler transformation, or maybe a source language feature, who knows, that is then able to figure out when it's worth using these things. And because Futhark is so generic, it doesn't know what a tensor is. It just knows about arrays of things, and it doesn't know what a matrix multiplication is. It just knows about maps and reducers. So it is kind of tricky to be able to utilize these extremely specialized things when the compiler doesn't really know what's truly going on. We also don't make very much use of warp level operations, only things that are essentially hard-coded in CodeGen, like our reductions and scans. They will do warp level operations, but anything that directly arises from user code will usually not do any warp level operations, which is unfortunate, because we must be leaving some performance on the table here. And of course, we don't have any transparent multi-GPU. I think that is really sad, because that should be, Futhark is high level enough that it should be possible to do this in a nice way, but we haven't gotten around to it. It turns out it is still tricky, because Futhark is still a little too expressive in some ways, so it can be difficult to do that efficiently. Okay, this is pretty much all that I had for today. If you think Futhark interesting, there are some resources that I suggest you look at. One is the Futhark book, which is a nice way of learning basic Futhark programming, and even some parallel algorithms, if you want to move beyond just smashing together tensors. I have a list of some various projects that use Futhark because it is a good choice. They decided it was a good choice for those projects. And in particular, recently a person made an LLM in Futhark. It's not a very good LLM. It's a GPT-2, but I thought it's pretty neat, and it shows how you can use the size types. It's very clearly shows the constraints of the size of different things. It's a very nice little program, but it does generate very good text. It's very repetitive in its output. There are some examples of small Futhark programs that show various various programming techniques. I definitely suggest looking at that if once you understand the basic syntax of how the language works. And then, of course, there's still a development blog that we've been writing for the past 8 or 9 years, which contains lots of information about things we got wrong, things we got right, weird optimizations, weird language features, and pretty much the life story of the language project. So that's it. That's what I had for my presentation.
Thank you, Troels. This was a wonderful talk. I see 2 questions in chat. Like, the first one is going to be by Vipul Sharma, and they're asking, like, could you comment on the landscape of functional programming support for GPUs in general? I think they're trying to get a sense of like how unique Futhark is in the space, or there's like other similar projects that inspired each other.
Yes, that is a very good question. So Futhark used to be less unique than it is now. When Futhark started, there was a good selection of functional languages that targeted GPU execution. The main one, the one to beat from our perspective, I mean, they're friendly, they're not our enemies, they are friendly colleagues, they were very inspiring, is Accelerate, which is a library for Haskell. It's an embedded language in Haskell. And that was kind of what we wanted to match and compete with initially. Accelerate is still around, but they focus more on multi-core CPUs now. Then there is DEX, which was a project by I guess Google Research, by some of the people who also made PyTorch, which is very similar to Fuzak in that it is an ML-like language with a rich type system for talking about multi-dimensional arrays, and they also have GPU code generation. Now, DEX is not maintained anymore, and it never reached the point where they actually said that you can use this for a real program, and we think it's a good idea. It was always a research prototype, and then I guess they got more interested in low-level, in kernel languages instead. I don't think there are any other functional GPU languages that are still around and are non-experimental. I mean, they're not super experimental. There's also one called Harland that hasn't been developed for 10 years. That was a GPU language that did everything. I mean, that had full recursion, everything you could possibly want in a functional language, and they could run it on GPU, but it would not run fast unless you walked the narrow path that was kind of invisible to the programmer. So but they show how you could just get it to run if all you wanted to care about was heating up the GPU. But I don't think there are currently any GPU targeting functional languages that are similar to Fuzak in its abstraction level. There are plenty that are more low level. I mean, you have lots of low representations here at GPU mode. And there are also some of them that are more high level, like PyTorch and GX to an extent. It depends on what you consider high level, of course. But for Fuzak's particular niche, which has higher order data programming, it's a pretty sparse field these days.
I will say, like, you do, I think, have still some spiritual colleagues that are doing low-level stuff, like specifically the team at like Colfax Research that like worked on a lot of like Flash Attention 3 and 4. Recently, like published a blog called "The Categorical Foundations for Qt Layouts." So I do feel like the ideas like are making a comeback, but it does seem to come and go in waves. It seems like.
Yeah, that's these tensor languages. You can really take a categorical approach to those. So the thing I dislike, I mean, they are very, very good for their purposes. But the thing that they don't do that I really wanted Fuzak to do was this idea that you can map anything you want. I mean, this parametric approach that you can have an array of things and you can map arrays of things, just like with a normal function language. That's kind of the dream of Fuzak, that whatever you map, the compiler should just make that run efficiently. And that is challenging, and maybe it's not even worth it. I mean, that's also an open question whether the thing that Fuzak tries to solve is a problem that very many people care about. But I'm an academic, so I'm allowed to dream.
But speaking of dreaming, like I think when you mentioned some of the challenges you had with distributed, I'm sort of curious if you could elaborate more, because like very naively speaking, I'd expect like purely functional and distributed would be like the sort of like match made in heaven. Like you kind of like have like in JAX, for example, things like VMAP or PMAP. But even then, if you're trying to express like specific kinds of parallelism strategies, it would be really nice if you could just be like apply parallelism, like apply expert parallelism on this dimension of this array, and like it just works. Like that sounds like the language of beautiful ergonomics.
It is very close to working, because the idea of having nested data parallelism is actually leads itself very well to distributed computation, because you can just distribute some of the other things to different GPUs, different machines in a cluster, and then you can kind of recursively distribute the inner loops as well in whatever way is appropriate. But the problem is that Fuzak has some constructs that make this super difficult. And the main culprit here is that Fuzak does allow you to do completely ad hoc random access of arrays. So at any time you can compute an integer, and then you can say, give me that element of an array. And that just completely wrecks distribution, because you have no idea what the communication is going to be like. And we really want the property that if you write a Fuzak program, then it will work on anything that the compiler supports. We don't want to just halfway through compilation say, oh, I can't figure out this index operation. Sorry, this program cannot run. And the reason is too complicated for me to explain. I don't want that experience. But again, I'm allowed to dream, so I want to only make promises that I can keep. And it turns out this promise is really, really hard to keep. But but we have some ideas. And part of it is restricting the language in some sense. So you have to. So it's more obvious too when you're doing something that will not distribute well, or to come up with some runtime mechanisms such that performance decays in a predictable way when you do naughty indexing. But if you behave nicely, then it'll just work. I'm okay with it being possible to write slow programs. I just want it to be pretty obvious when it happens.
All right, and I guess like my last question before I let you go. So, I think like Futhark has something to do with like Norse ruins, like as like a name inspiration. Could you like speak to a bit like where the name came from?
Yes, definitely. I forgot. Do I have it here? No. Okay, but I'll run the REPL then, because this is these are the first 6 letters of the runic alphabet, and they spell out F-U Thorn A-R-C. So Futhark. It's just the first 6 letters of the runic alphabet, which is also then the name of the runic alphabet. And it turns out people who name alphabets are really unimaginative, because even alphabet is just alpha beta, so it's just the first 2 letters. All alphabets are named like that. It's very they're not really very creative.
All right. Well, Troels, again, thank you so much for coming. It was a pleasure having you. We'd love to have you back, so you're more than welcome anytime you feel like it, you or any of your students. So thanks everyone for watching. And if you have any questions to Troel, he's fairly active on the GitHub for the Futhark repo, so just feel free to ask him questions there.
Yes, pleasure to be here.
Thank you. Thank you. Bye-bye.
Welcome.